Okay, so we have another kind of vector product, which is obviously you know this is a cross product between two vectors u and v. We denote it by this cross. Now we also know that the cross product is not commutative. So if you change the order of u and v, you get minus v cross u. The result of a cross product is a vector. And then there are a bunch of properties which you probably are aware of. Cross product is associative, so u cross v plus w is equal to u cross v plus u cross w. Uh, One important thing here is the last equation here. The last equation is called a vector triple product. So it's a cross product between two vectors dotted with another vector. So what you get from this is called a vector triple product, and what you get from this is a scalar. And this has some properties which is written here. Uh, you can change the order of these three vectors u, v, and w in a particular fashion. So you bring the v out, you take the u to the end. This gives you w cross u, and then you bring the w out, you take the v to the end, and this gives you w dot u cross v. So basically you have to rotate these three vectors in a clockwise fashion in order to get the different uh, uh, equal results from a vector triple product of three vectors. So this is all we know about the cross product. And now I will define something called a permutation symbol. I'll define something called a permutation symbol, just like we have defined the Kronecker delta, as a bunch of numbers with three indices now, I, j, and k. So I can go take values of 1 to 3, j can take values from 1 to 3, and k can take values from 1 to 3. So there are 27 such numbers, 3 cross 3 cross 3 into 3 into 3. So 27 such numbers that need to be defined to define Eijk completely, and this is the law that we will use. So Eijk is equal to 1 if I, j, and k form a clockwise permutation. So I, j, and k clockwise means 1, 2, 3 is a clockwise permutation, 3, 1, 2 is a clockwise permutation, 1, 2, 3, 3, 1, 2, 2, 3, 1, these are clockwise permutations and they will give a value of 1. Anti-clockwise permutations, so 1, 3, 2, 3, 2, 1, 2, 1, 3 will give you minus 1, and all other cases where either I, j, or k are the same will give you 0. So all cases where any two of these three indices are the same will give you 0. Clockwise would give you 1, anti-clockwise would give you minus 1. This is the law that defines the permutation symbol, just like in case of the Kronecker delta. Now, this is useful in working out the cross product of the base vectors. So if I take any two base vectors, e, I, e, j, uh, I get either ek or minus ek or 0. When do I get 0? Obviously, if I take e1 cross e1, I will get 0. If I take e1 cross e2 in a right-handed system, if I take e1 cross e2 in a right-handed system, I will get e3. If I take e2 cross e1 in a right-handed system, I will get minus e3. So this is a general rule for cross products between the base vectors that is always valid. If I take cross product between the same vectors, I get 0. If I take a clockwise permutation, I get minus. If I take it anti-clockwise, I get a positive number. So so this equation can be succinctly, in a very concise manner, written in terms of this permutation tensor. So permutation symbol, we will not call it a tensor as yet. It's a permutation symbol which we have defined in this manner. So we can write this as EI cross EJ is equal to EIJK EK. Now you can keep putting in the values of EIJK according to this rule into this equation to see that this will actually reproduce this long equation. So this long equation can be concisely written in terms of the permutation symbol given the definition of the permutation symbol given here. So let us look at one case. E1, I is 1, J is 2. I should get E3. So E1 cross E2 will be E1 to K EK. Now E1 to K, there's only one positive symbol, positive permutation, 1, 2 and 3. 1, 2, 3 is the only positive permutation and that will give you 1. So 1, 2, 3 is the only positive permutation and any other combination of IJK will give you either of I or J to match with K. So for example, you can have 1, 2, 2 which will give you 0 and 1, 2, 1 again will give you 0. So the only non-zero contribution will come from 1, 2, 3. And that non-zero contribution 1, 2, 3 is a clockwise permutation and therefore its value will be 1. So the only possibility is E1 cross E2 is equal to E1 to 3 E3. E1 to 3 is 1 and E3 remains. So E1 cross E2 will be equal to E3. Now take E2 cross E1, E2 cross E1. So I is 2, J is 1 and you have 2, 1K EK. In 2, 1K, the only non-zero contribution is 2, 1, 3. 2, 1, 3. That is a counterclockwise permutation, so its value is -1. Any other combination, 2, 1, 1, 2, 1, 2 will give you 0 according to this rule. So you will get 2, 1, 3 E3 and 2, 1, 3 is equal to -1. So you get E2 cross E1 is equal to minus E3. So this is satisfied if I use the permutation symbol in this manner. So now having learned the permutation symbol and the Kronecker delta, we will be able to work with vectors quite efficiently. So let us take a problem and let me try and work this out with this fancy thing that I have, fancy tablet that I have. Okay, so so what I am going to show you is how to work out, for example, the cross product between two vectors in indicial notation, how to work out the dot product, and how to work out the vector triple product. Let's call the vectors W, U, and V, and then let me try to work this out. So you have, let's say W is equal to U cross V. So you start from here. So U cross V is going to give you a vector W, and you want to find the components of W. Okay, so what we do is we write U as, let's say, UM EM. Okay, we write V as VP EP, and then we can write U cross V as UM EM cross VP EP. Okay, and this UM and VP are the components, mth component and pth component of U and V respectively. They are scalars. So I can write UM VP EM cross EP. Now from the definition of the permutation symbol, I know that EM cross EP is same as, let's go back. So the definition of the cross product, we know that EM cross EP will be uh, MPKEK. Okay, so EM cross EP will be EMPK UMVPEK. So the kth component of W, so WKEK will be given by this. I am messing it up, but this is what it is. This is the final expression that we get. So W is a vector whose components are the permutation symbol MPK UMVP. So its kth component is EMPK UMVP. Now so WK, the kth component of W, is EMPK UMVP. Now here you will notice that M and P are repeated indices, so we'll write them as EJKI. So I have changed, this is not a repeated index, this is a free index, so I have to change it on the other side as well. So WI is EJKI UJVK, and now if you look at MPK, a clockwise combination is, let's say MPK is a clockwise combination, then KMP is also a clockwise combination. If MPK is an anti-clockwise combination, it's also anti-clockwise. So I can just write this as IJK UJVK. So in place of MPK, I have written KMP, which is also clockwise, and UMVP. And then when I replaced K by I have IJK, UJVK, J and K are repeated indices, I is the free index. So the ith component in a cross product, what we have shown is in a cross product, the ith component of W is EIJK UJVK, or we can write WIEI as a vector is equal to EIJK UJVK EI. This is also possible. Okay, so this is how we deal with the cross product. Let us see how we deal with the dot product. So we know that U dot V will give me a scalar. So you write U as, again, UM EM, repeated indices, I can use anything, M, M, N, P, whatever, dotted with VP, EP. So I write P here and M here because I cannot repeat a repeated index more than 2 times. So I have used it 2 times here, I have to use something else here. So then UM and VP are scalars, so come out. And then you have EM dot EP. Okay, from the definition of the Kronecker delta, we know that UM VP and EM dot EP is delta MP, Kronecker delta MP. Now, this is where the fun starts. You have this delta MP here, and then it has the property that when m is equal to p, it's equal to 1, and when m is not equal to p, it's equal to 0. So what this will do, you can open this up, you can write 1, 2, 3 and open this up. M and p both are repeated indices, and when you open it up, you will see that the role of this delta will be to knock off one of these two indices that are common to it by the other one. So if you want to knock off p, you will have to replace it by m. If you have to knock off m, you will have to replace it by p. So you have two options to write it as umvm. So here I have knocked off p, or you have another option to write it as UPVP. In both cases, you see that M is a repeated index, P is also a repeated index. So the meaning of this expression and this expression are exactly the same, which means that U dot V is a scalar given by, let's say, VK UK or UMVM. Both are the same. So the cross product is given by cross product. The kth component of the ith component of the cross product is given by Eijk UJVK, and the dot product is given by UKVK. So dot product between two vectors is a scalar. This is a vector because you have a free index I, so that makes it a vector, and you don't have any free indices here, so that makes it a scalar. Let's look at the triple product now. So the triple product is, let's say, the triple product between W dot uh, U cross V. The triple product is a scalar, so we will write it as, again, we'll break up the vectors into components. We'll write it as, let's say, WM EM dotted with U, let's say PEP crossed with VQ EQ. Okay, so this is equal to WMEM remains dotted with. Now we have already worked this out, so this will be E. So the ith component of this vector, let's say, will be EIPQ UP VQ EI. So this will be the ith this part is the ith component. This part is the ith component of this cross product, and because it's the ith component, I have to write EI here. So this is the net vector that results from U cross V. Now I have to dot this with this guy. I have to dot this with this guy. So I have EIPQ WM UP VQ, all of these are scalars, and then I have EM dot EI, which we know can be replaced by EIPQ WM UP VQ delta MI. Now delta MI will either knock off this M in favor of I, or this I in favor of M. So let us knock off this I in favor of M. Then what I have is E M P Q W M U P V Q. All of these are repeated indices. M, P, Q are repeated indices. So what you have is a scalar, and because it's a scalar, I can write this as, let's say, E I J K W I u j v k. This is also equally valid as this expression. So this is how you work with vectors and use the permutation symbol and the Kronecker delta to what figure out the various vector identities that we already know. Okay, so this was the problem. Now we have another thing called the E delta identity, which is a relationship between E and delta. It is easy to prove from a vector identity, but we will not prove it. So what it says is Eijk, Eimn. Remember, I is the repeated index. Jk, Mn are free indices. They are not, only the first index is repeated. Is equal to delta Jm delta Kn minus delta Jn delta Km. The way to remember this order is that the first one is, if you write the indices like this, I, j, k and I, m, n, I is repeated. Then the first one is first times second. So first is j and m. So first are j and m in the two groups. The first is j and the first is m, into second is k into n. The second are k and n. And then outer times inner. So outer is Jn, these are outer, J and N are outer, and inner ones are K and M. So K and M. So first into second minus outer into inner is how this E delta identity can be remembered. So this is the E delta identity which we will need to manipulate expressions containing vector identities. So I'll now go over to defining what a second order tensor is. We have talked about vectors so far. So while I go to second order tensors, you still have to remember the Kronecker delta and the permutation symbol. With that in mind, let us define a second order tensor. As I have said, a second order tensor, we will denote it by a capital bold letter. And a second order tensor is a quantity that acts on a vector and gives another vector. So this is a linear transformation. You might have learned of linear transformations in your linear algebra courses. So this is a linear transformation which takes a vector and gives you another vector. So this is a quantity that does that linear transformation, and like all linear transformations, it is linear, which means that t applying on alpha u plus beta v, alpha beta are scalars. So if it applies on this combination of scalar combination, linear scalar combination of these two vectors, then you get alpha tu plus beta tv. And they also obey these rules. A plus minus b on acting on u will give you two vectors, au plus minus b, bv, bu. Or if you multiply it by a scalar, the scalar comes out and you have au times the scalar. So these are obvious rules. The thing to remember from here is a second order tensor acts on a vector and gives you another vector. So a second order tensor can also be generated by, if we define a new kind of product between two vectors. So let's take two vectors a and b, and we define something called a dyadic product of a and b, and we say that this dyadic product is not the dot product or the cross product. This is a little different from the cross product because you have a cross with a circle. So this is a dyadic product of two vectors, and the definition of a dyadic product of two vectors is it acts on another vector. This dyadic product is defined as something that acts on another vector according to the rule given here. So A dyadic B is a quantity which acts on V to give you B dot V, which is a scalar, times A, which is a vector. So dyadic product acts on this vector V to give you another vector which is A scaled by B dot V. Okay, so the right hand side is a vector This dyadic product acts on a vector to give you another vector. Therefore, the dyadic product is a second order tensor, because we have defined second order tensors as something that acts on vectors to give you vectors, and the dyadic product does exactly that. So the dyadic product of two vectors is called the tensor product of vectors, and it acts on something to give you, acts on a vector to give you another vector. Okay. uh, so um, One thing that we need to note is that, like the cross product, a dyadic product is, you cannot interchange the order of the two vectors. So A dyadic B is not the same as B dyadic A. Dyadic product is a tensor, but you don't get the same tensor if you do B dyadic A as you get when you do A dyadic B. So uh, the idea is this. The idea is that if we have a vector, which is also called a first order tensor, then any vector can be written in terms of its components in a Cartesian system and the Cartesian base vector. So Vi, Ei, I is a repeater index. So EIs are the basis in which a vector V or any vector can always be expanded. So these are the bases. For second order tensors, so second order tensors, remember, are defined by this relation. Second order tensors act on vectors to give you vectors. With that definition in mind, any second order tensor can now be expressed in a basis space which is spanned by the dyadic products between the basis vectors. So these are the basis vectors. These are dyadic products between the basis vectors. Ei, dyadic Ej are dyadic products between basis vectors. And these dyadic products, there are 9 of them, because I can go from 1 to 3, J can go from 1 to 3. There are 9 of them, and these 9 of them together form the basis vector space, which can be used to represent any second order tensor in the Cartesian coordinate system. So Tij are the components of the Cartesian tensor, second order tensor T, in the same way as Vi are the components of the Cartesian uh, vector expressed in the Cartesian coordinate, vector V expressed in the Cartesian coordinate. So VI's are the components of V expressed in a Cartesian coordinate system. Tij are the components of a second order tensor expressed in the Cartesian coordinate system. For a second order tensor, the basis is Ei dyadic Ej, and for a vector, the bases are Ei only. Okay, so this is how every tensor would be can be represented, and this is how every vector can be represented in a Cartesian system. And what you have, the scalar that you have, scalar multiplier that you have, will be denoted by Vi in case of a vector, Tij in case of a second order tensor. Now there are 9 components of T. So T is a second order tensor. It has two indices, so it has 9 components. A vector has 3 components, as we know. Now, with this definition in mind, um, and the definition of a dyadic, there are a few things that we can now, the properties of second order tensor that we can enumerate. So A plus B is equal to B plus A. There's a zero second order tensor, sorry. There's a zero second order tensor which you can add to any tensor, second order tensor, to get same tensor. There's a negative which gives you 0 when added to A. Minus A will give you the 0 second order tensor. It is commutative. You can add them in any order you like. You can multiply it by a scalar. You get scalar times, you can do AB times C, and the order doesn't matter. So you can do B and C first, then multiply with A, and AB first, then multiply with C. You get the same result. And um, you must note that there are these are similar to what you had learned for vectors, except that there are a couple of important differences that you should know. Firstly, a times b is not the same as b times a. A times b is generally not the same as b times a, and a times b equal to 0 does not necessarily mean that a is equal to 0 and b is equal to, or b is equal to 0. Similarly, when a multiplied by a vector is equal to a 0 vector, remember a second order tensor multiplies a vector to give you a vector. So this is a 0 vector. When a multiplies a vector to give you a 0 vector, it does not mean that either a is equal to a 0 tensor or u is equal to a 0 vector. So these are important caveats that you must remember that are different from vectors. Other than that, these are rules that any linear transformation has to obey, as you might have learned in linear algebra. So these are the rules that any linear transformation obeys, except that there are these small caveats that you have to remember. Okay, now how do we operate with second order tensors? So one way is, let me go back to my, okay. So first let us see how we get uh, the components of a vector out. Suppose I have a vector v. Okay, I want to know the ith component of v. What do? I dot it with ei. Okay, why do I dot it with ei? Because it's simple. I can write v as vm en and then dot it with ei. So I get Vm delta Mi. So now M will get knocked off in favor of I, so I'll get Vi. So if I dot V with Ei, I get the ith component of V out. If I wanted the jth component, I would dot it with Ej. Similarly, for a second order tensor, if I want to get its, say, ijth component out, I want to get the ijth component of a second order tensor T. This is what I will do. I will first multiply it by j. So I will do this post multiplication by j. This is post multiplication by j. So remember, uh, this is a second order tensor. This is a vector, so the result should be a vector. Now write T as Tmn Em dyadic En. Remember, these are the basis vectors. These are the bases for any second order tensor. Multiply with Ej and now use the definition of a dyadic product. A dyadic product times a vector gives you another vector. So this will give me Em times En dot Ej. So this just follows from the property of the dyadic product, which will give me Tmn Em delta Nj, which now j n will be knocked off in favor of j. So I'll have Tmj En. This is what I'll have if when I post multiply it by Ej. Now I pre-multiply it again by Ei. So Ei dot Tej will give me Ei dotted with, I already know how much this is. This is Tmj Em, which will give me delta ij Ei dot sorry delta, so delta Im Tmj. So this delta will knock off this m in favor of the I, so I'll get Tij. So to get the ijth component of a tensor out, I have to pre-multiply it with Ei, post-multiply with Tj. So Tij is equal to EI pre-multiply with E. Okay. Now, remember, just look at two things. One, I am using a dot here because this is second order tensor times a vector, which is a vector. So this is a dot product between two vectors. I'm not using a dot here because this is second order tensor operating on a vector, and this operation always leads to a vector. That is evident from the context. So I'm not writing a dot here. Whenever I have a second order tensor multiplying a vector, I'll never put a dot. But when I have vectors multiplying vectors, same kind of quantities multiplying same kind of quantities, I will have to use some kind of a symbol because otherwise it gets confusing. Okay, so uh, let's go back to the slides. So let us now derive the ijth component. We know how to extract the ijth component. So let us now derive the ijth component of u dyadic v. U dyadic v. Let us do that. So you want to do, you have u dyadic v, which is a second order tensor, and you want its ijth component. To do that, what you will have to do, you will have to post multiply with j and pre-multiply with I. Pre-multiply with I. So that will give you ei dotted with, let's write this as em dyadic of, let's say, vp ep times ej. Okay, so this is ei dot um vp, and then you have this dyadic product em cross ep times ej, and this, so this dyadic product from the definition of dyadic product will give you em times uh, em into ep dot ej, right? So this is now ei dot um vp, and this is em times delta pj, and this p can be knocked off in favor of j. So what I will have is, and I have this ei dotted with em, which will give me delta mi, and you have um vp times delta pj. So that will be I m will be knocked off in favor of I, p will be knocked off in favor of j, so you will be ending up with ui bj. So the ith component of u dyadic v, the ijth component of u dyadic v is simply ui bj. That's what we have proved. So uh, u dyadic v is indeed a tensor, second order tensor. Its components are ui vj. Remember, u I and j both are free indices, so this is actually, this represents a set of 9 numbers. Right? This represents a set of 9 numbers. This is not a scalar. There's no summation here. This is not repeated. So if it were repeated, it would become like a dot product. That's not the case. They're not repeated. So it's a set of 9 numbers, 9 different numbers representing the components of this second order tensor u cross v. Okay. Okay. Now for uh, okay. So another thing that we have to remember is we have something called a second order identity tensor I, whose components are delta ij. So delta ij are the components of I. So I is like delta 1 1 e 1 1. So the first 1 1th component is 1. Then you have two zeros. Then the 2 2th component is again 1, and 3 3th component is again 1. All other components are 0. So I is a second order tensor, and its components are delta ij. Okay. Let me stop here for this slide.